Hello everyone. I'm Dr. Kushal Roy, Assistant Professor of Mathematics of Dr. B.C. Roy Engineering College. So I am continuing a lecture series on complex analysis and analytic function. So the definition: a function f is called analytic at some point z naught belongs to C. C means the set of complex numbers if there exists some r greater than 0 such that f is differentiable at every point z belongs to the open ball centered at z naught and radius r. A function is called analytic in an open set U if it is analytic at each and every point of U. An entire function is a function which is analytic on the whole complex plane C. Okay, so for some n belongs to capital N and complex numbers a naught to a1, the polynomial fz, which is defined by a naught plus a1z plus a2z square plus dot 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 plus n z to the power n, which is entire function. The function fz equal to 1 by z is analytic for every z not equal to 0. At z equal to 0, this function is not defined, therefore it cannot be analytic. Analyticity is clearly implying differentiability, but there are some differentiable functions which are not analytic. For example, a function fz equal to mod z square, it is differentiable only at z equal to 0. However, it is not analytic at any other point. Let fz equal to u plus iv, where u and v are the real and complex part of f respectively, and f is defined on an open connected subset D of the complex plane. Then f is analytic on D implies f satisfies CR equations on D. CR equation means del u del x equal to del v del y and del u del y equal to minus del v del x. If satisfies CR equation on D and U and V has continuous first order partial derivatives on D implies F is differentiable on D and therefore F is analytic on D. So therefore the second one is a sufficient condition show that F may be analytic. Suppose F and G are analytic in an open set D, then clearly F plus minus G, F into G, these are analytic. Also, F by G is analytic if G is not equal to 0 on D. And similarly, any constant multiple of that these analytic functions are analytic. So, for example, alpha into A is analytic. Composition of two analytic functions is analytic. Let F be analytic in a domain D if the real part or imaginary part or argument or modulus of f is constant, then clearly f is constant because of the CR equation. Now, harmonic functions. A real valued function phi is said to be harmonic in a domain D if all the partial derivatives up to second order exist and continuous on D, and f satisfies the Laplace equation del 2f del x2 plus del 2 phi del x2 plus del 2 phi del y 2 equal 0 at each point of view. A theorem, let f if fz equal to u plus iv is analytic in a domain D, then the functions u and v are harmonic in D. Okay. It can be easily proved using the CR equation because ux equal to vy and uy equal to minus vx. One can easily show that uxx equal to vyx and similarly uyy equal to minus vxy. And since these partial derivatives of second order partial derivatives of v are continuous, therefore vyx and vxy are same. So therefore uxx plus uyy equal to 0. In a similar way, we can show that vxx plus vyy is equal to 0. Let D be a domain and U from D to R be harmonic. Does there exist a harmonic function V which is defined from D to R? So show that fz equal to U plus IV is analytic in D. If such harmonic function V from D to R exists, then V is called harmonic conjugate of U. The function v equal to 2xy is a harmonic conjugate of u in C. The function fz equal to z square, which is x square minus y square plus I into 2xy. It is clearly analytic in C. Does harmonic conjugate V always exist for a given harmonic function U in a domain D? Answer is no. For example, the function U, which is the log of square root of x square plus y square, is harmonic in G, which is C minus 0, and that means the punctured complex plane C, and it has no harmonic conjugate on G. Now the question rises, under what condition harmonic conjugate V exists for a given harmonic function U in a domain D? The theorem is here. Let G is either the whole complex plane C or some open disk. That means some open connected subset. If U from G to R is a harmonic function, then U has a harmonic conjugate in G. Now, how do we construct the harmonic conjugate? Construction of the harmonic conjugate, just if say if u equal to x square minus y square, we have to find the harmonic conjugate of u. So first we have to check whether u is harmonic. Then we have to calculate ux and uy. We have to use ux and uy in CR equations so that we can get vy and also vx. From vy, by integrating v partially with respect to y, we can get v. And similarly, by integrating that now by differentiating v partially with respect to x, we can get some form for vx. Now we have to just actually compare vx, this value of vx, with the given value of vx, and in that case, we can easily get the final form of the function. Now, given a harmonic function u, suppose the harmonic conjugate of u exists. Is it unique? Yes, it is unique up to an analytic constant. So therefore, if a harmonic function is given, its harmonic conjugate is unique. Up to an analytic constant means we can add some constant to that function. Okay, so a function f, which is u plus iv, is analytic if and only if v is the harmonic conjugate of u. It is very, very simple. If f is analytic, then v is the harmonic conjugate of u. And if v is the harmonic conjugate of u, then fz equal to u plus iv is analytic. Okay. So this is the end of today's lecture. Thank you everyone for attending my lecture.